Okay, so first we're going to work with this F chart to calculate the performance of solar collectors. This is what we are going to do. But first, we have to analyze the system. Okay, so if we want to analyze the system, we need to understand what we are doing. We can use solar collectors just for domestic hot water. That's the first option. We have to calculate the amount of hot water that we need in our building, and then we have to dimension our solar collector array. Or we can integrate the system with the heating system. This is more complicated, more effective, probably, but yeah, more complicated to. It's just the installation. It's more complicated because we have to integrate two different systems with the same solar collector. And then the third option, and probably is the best one, we can have solar collectors for domestic hot water. We can have solar collectors for helping or, yeah, so to collaborate with the heating system. And we can use solar collectors to heat up swimming pools. So this is the most effective way, because with if we can heat up swimming pools in summer, we prevent this problem of overheating from happening. Okay, so first we have to make a decision. Installing solar collectors is good, it's cheap, it's reliable, especially if we don't have freezing temperatures, and it's very effective. So first, we need to understand the kind of installation that we need. So I'm taking this from the Department of Energy. Okay, so we need a reliable source, and let's assume that the Department of Energy is a reliable source. You have this website here. Okay, so if we are here sizing a new water heater, so there are different things about water heaters. We need hot water. Okay, so especially in residential buildings, we need hot water. We can have different options. We can have the tankless or demand type water heaters. What is it? It's a device that just, if we click here, this is the device. Okay, so we have a small device close to the element in which we need a water heater. In this case, it's sink or the shower or whatever. It's electric. Okay, so we have an electric resistant here, and we introduce cold water. The electric element heats up water, and we return hot water, and then that hot water goes to the tap or to the shower or whatever. So with this case, we don't need any storage tank, and we don't need any water collectors. Okay, so this is probably the easiest way to generate hot water. What's the problem here? Well, the problem, it's electric, it's not a problem, but we need to understand that we are working with electricity. So we have to add this electric demand to the electric demand of our building. Okay, so we have computers, we have electric lights, and if we are using this device, we are using an electric water heater. And we have to calculate the maximum amount of water, of hot water that we use, and we have to dimension this accordingly. Okay. We have advantages and disadvantages. The main advantage is that it's very straightforward. Okay, so we have a source of hot water, we install the device, and it heats up the water immediately. We don't need pipes, we don't need solar collectors, we don't need storage tanks. It's very straightforward. The downside of this, well, a disadvantage, probably in terms of energy usage, it demands more energy. And it demands electric energy. So we can have PV panels to generate the electricity that we need to heat up the water. But then we have to, okay, so when do we need hot water? Usually in the morning, when all the family wakes up and we prepare the children to go to school, or we go to our workplace or whatever, This is the moment in which we need more energy. And usually it's early in the morning and we don't have sun. So we cannot use the energy from the sun. We're using PV panels to heat up this. Okay, so integrating this with renewable energies, complicated because unless we have batteries or something like that. So that's the main disadvantage. Well, it's a disadvantage. It's just we need to know how it works. So if we have an electric device, we need electricity. We're not going to study this today, okay? So we are going to study the sizing a solar water heating system. So the solar water heating system, it's something like that. We have a solar collector, and then we have a water tank. And then the water tank, we have a cold water supply. And then from the water tank, we have the hot water. So this is what we're going to study today. And this is the solar collector. This is the renewable energy device that we're going to install. There are two different systems here. We have the direct circulation system or the indirect circulation system. The first one means that the water that goes through the solar collector, the water that we heat up in the solar collector, is the water that we use in the shower or in the sink or in the dishwasher, wherever we need hot water. That works well in climates where it rarely freezes. So in warm climates, we don't have freezing temperatures, it works well. But we are in New England, so this drawing is a better option. So we have the indirect circulation system. That means that the fluid that goes through the panel is not just water, it's an antifreeze fluid. Okay, so this is what we have here. So it's not water because we can have freezing temperatures. So to prevent frozen pipes, we don't circulate water through this, we circulate this antifreeze fluid. So how do we select this fluid? It depends on the minimum temperature that we can have outside. If the minimum temperature that we have in New Hampshire is -20 Fahrenheit, we need a fluid that doesn't freeze at -20 Fahrenheit. Does it exist? Yes, it exists. But we need to know that, okay? So if we don't select the right antifreeze fluid, we will have some trouble. So this is what I recommend, but again, we need to know the minimum temperature that we can have throughout the year. It's not the average, it's the minimum temperature, because if we have only a few minutes with this minimum temperature, the pipes can burst, okay? So we have to be careful with that. But other than that, other than knowing, this is very efficient because we don't circulate water through this, and then we heat up this fluid, and then through this loop, then we release the heat to the water tank, and then we heat up the water in the water tank. Okay, so this is what we're going to use now. This second option, not the first one. And okay, so once we know what we are doing, we need to select the collector area. So what is the collector area? What is the recommended collector area according to the Department of Energy of the United States? Okay, so we have a guideline or a rule of thumb of around 20 square feet of collector area for each of the first two family members. Okay, so 20 square feet for per two family members. And for every additional person, 8 square feet if you live in the US Sun Belt, or if you live in the northern United States. Well, quite complicated. Anyway, it's like 20 square feet for two first family members. So if we have a couple, that would be 40 square feet. And if we have 3 people, a couple and son or daughter or whatever, it will be 20 times 2, 40, plus, if we live in the northern United States, 12 to 14. So it will be 55 or 54, 55. Okay, is that clear? So if there are 3 people, we will have around 55 square feet. If there are 4 people, we will have 40 plus 30, around 70 square feet, something like that. It's a rule of thumb. And then the storage volume. So that is, I would use this. We need 2 gallons of storage to 1 square foot of collector area. So that's the rule of thumb. Okay, so we can write it down. So we are dealing with solar collectors. Collector area. We need 20 times 2 plus, let's say 14 times number of children. Let's assume that we live in a traditional family household. And this is the couple. So we have 40. And the units are square feet. Okay. So if we have a couple, we have 40 square feet. If we have a couple with 2 children, we have 40 plus 14 times 2. So around, yeah, around 70 or 68 or something like that. Okay, so that's the collector area. Then the storage. The storage is 2 gallons times collector area. Okay, so those are rule of thumbs. We can, in single family houses, we can work with this. What if we have a different buildings? Well, if we have different buildings, we would need to know the hot water demand of different buildings. Hot water demand of commercial buildings. I'm looking for just a table in which we can have the hot water demand here. So we can have different sources, but well, what are we? This is the estimated hot water usage, gallons per person per day. Okay, so we can copy this. And with this table, we have the estimated hot water usage per person and per day. Look at this. If we are in houses, motels or hotels and hospitals, we have a huge hot water consumption. If we have in office buildings, school buildings, it depends. If we have showers, the hot water consumption increases. If we don't have any showers in office buildings or in schools, the hot water demand is not that much. Okay, so we are using this for residential buildings or for hospitals. if we have gyms or winter swimming pool, we might have, again, something very, we might have a high energy consumption, but most likely we use this kind of devices for residential buildings, for hotels and hospitals, because this is where the hot water demand is more. Okay, so this is it. We have the collector area, we have the storage. So with this, and if we are in commercial buildings other than houses, we have here some, this is the hot water usage in gallons per person per day. Okay. What else do we have here? Sometimes we need to estimate the peak hour demand. Okay, so what is the peak hour demand? There's a moment, or there's a moment in which we have the peak demand in a single family house. It's usually first hour in the morning when everybody's waking up and having a shower. This is the peak demand. Then the rest of the day, probably we don't have any hot water usage. If we have lunch and we cook, probably we need, there will be another peak, but usually for cooking, the amount of water that we need is less than for having a shower, okay? So this is, here we have, for the shower, we have the average gallons of hot water, 20 gallons per shower, for shaving, for dishwashers, and clothes washer, whatever. Okay, so here we have if we need this element, if we need this, what is the peak? If we have 3 showers, 1 shave, and 1 hand dishwashing, that would be the peak hour demand. Sometimes we need this value, especially if we are using the first system that I showed you, the tankless or demand type water heaters. Okay, so in this case, we need the peak, because if we have 66 gallons early in the morning, we need a system that can heat up 66 gallons at that time, okay? But I told you that now we are using the storage system. Okay, so first, if you are dealing with a house, if you are dealing with hotels, or if you are dealing with apartment buildings, in apartment buildings, you can use this number, like 20 gallons per person per day. So it depends on how many bedrooms. How many people do we have in the house? Usually the number of bedrooms times 2. Okay, so if we have 2 bedrooms, we have to dimension the system for 4 people. If we have 3 bedrooms, we should dimension the system for 6 people, something like that. Okay, so once we have the demand, with the demand, we can have the collector area, and then we can have the storage. So imagine that we have 4 people. The solar collector area would be 40 times 28, so 68 square feet. And the storage would be 2 gallons per collector area. So it's 136. Okay, so imagine that we are dealing with a 4 people single family house. That would be a 2-bedroom single family house. So those are the numbers that we're going to use. Okay, so let's start using the F-chart software. Number of collector panels and collector panel area. Okay, The collector panel area, by default, we have 20 square feet. 20 square feet is, it's the average. I mean, there is not much creativity when it comes to the solar collectors. Most of them are the same, and probably because it's the most efficient size in terms of manufacturing, and people can handle a 20-foot collector area, but if it's bigger, probably they would need more people. So probably if we have this area for most of the collectors, it's because it's the most efficient one. So if we need 68 square feet and each collector area is 20, and each collector is 20 square feet, so how many of them we need? Like 3, it would be 60. So let's say 4. Okay, so we have 4 collectors times 20 is 80. If we need 68, so that's. And then what about the storage? Now we don't have 68. We came up with 80 square feet. So now we don't have 136 gallons. We have 160 gallons. Okay. So we can have the first assumption, but then if we change the numbers because we round up things, or we can have exactly 68 square feet because we don't have these devices in the market. So we have to round up here, and then we have to recalculate the storage area. Okay, so we have this. Where do we have the storage area? Okay, sorry. Before doing that, we have to select the system. Okay, so let's go over step by step. We have here edit. Basically in edit, we can't do anything. Preferences, let's use international units. No, English units, sorry. You see, if we change to international units, here we have square meters and watts. If we're working with English units, let's work with gallons and square feet. And system is the most important thing, okay? By default, I don't know why it has the pool heating. So we will use this option, but later on. So far, we want the first option, and the first option is active domestic hot water, okay? So make sure that you select this system, active domestic hot water. It's just we're using this to heat up water. We're not using this for the heating system or for pool heating. It's just for domestic hot water. Okay, select this. What about the collector? We have the flat plate or evacuated tube. I talked to you about the difference between the flat plate collector. We have this device, which is very efficient, very easy to manufacture, ugly. Yeah, people usually don't like this kind of flat plate collectors. Okay. Well, it's not something that we are proud of, so we usually don't show the solar collector. It's not. And then we have the other option is the evacuated tube. So if we use the evacuated tube, this is different. Okay, so I spoke about this option last week. So we have these glass pipes. We have vacuum inside the glass pipe, and there is a fluid. So the technology to manufacture these pipes, it's more advanced, it's more complicated. And well, usually we like it. Architects like it because, well, it looks fancy. So you are not ashamed of showing this in your building because it looks like it looks better. than the evacuated, like the flat plate collector. Okay. Anyway, those are more expensive, more efficient. So for this first exercise, we can use the flat plate. And then we have the compound parabolic and axis tracking. I wouldn't use this, okay? What is the compound parabolic collector? It's something like this, okay? So it's a device, yeah, this is it. So it's a parabolic mirror, and then every sun that it's reflecting on this mirror, the reflection lines goes up to this pipe that we have here. And well, we can heat up this pipe. We don't have water. We have another fluid. So by having those long parabolic collectors, we can heat up we can heat up this fluid, okay, and then we heat up water. The water boils, and we have steam, and the steam moves. Okay, we can have this, but we don't use this for residential buildings that I know of. Okay, so this is very effective when we have solar farms, and we have those. We have these solar plants, gigantic solar plants, and okay, so that works well at a large scale. In buildings, I don't, and that it makes sense that we have a tracking because we can track the sun and we can increase the effectiveness of the device itself. But we don't have these kind of things in single family houses so far. Maybe in the future we will, but it's very unlikely. And yeah, so that's another option. We will explain about this later, but that's another option that we can do with these parabolic mirrors. But yeah, so this is what the compound parabolic collector means, and then we can track it. We can track the sun, but for single family houses or for buildings, we're going to use either the flat plate or the evacuated tube, okay? And then the weather, select data location. The only thing we can do is to select the northeast, northwest, south central. Let's select northeast. It changes here automatically to the northeast. And run plot, we have to change all the parameters here, and then we will run and plot the results. So we are going to do that very quickly. So we have selected the number of collector panels. We have 4 times 20, so that's 80 square feet. Then here we have the water volume per collector area. We have 2 gallons per square feet. This is what we have here, 2 gallons per collector area. So that's the rule of thumb, okay? So we don't have to change this because we only have to change the area, the number of collector panels. We usually don't change the collector panel area. We change the number of collector panels. What is this? So those are parameters that depend on the collector itself, okay? So this is the efficiency of the element. This FR times UL, okay, times alpha. So that speaks about the efficiency of the collector. In this case, we have 0.74 or 0.7. Yeah, so 70% of efficiency. It's the average for this. Probably if we change the collector to the evacuated tube, that will change. We have other values here, okay? So we can go to the specifications of the collector, but for the for this flat plate, 70%, 70 to 75%, it's something usual. So I wouldn't change that. Then we have the collector slope. That's important, okay, because that affects the efficiency of this. So that depends on the roof or whatever. So by default, we have 45. That's type 30. It depends, okay. The collector azimuth, south equals 0. Again, it doesn't make any sense placing this with a different azimuth. So if we are placing this on the north facade, we won't have any hot water. And placing it in the east or in the west, it will affect. So let's place it in the south if we can do that. And what else? Collector to flow rate area and collector fluid specific heat. Okay, so this depends on the fluid that we are using for to run through the collector. If we are using water, those numbers will change. If we are using water with this anti-freeze fluid, those numbers will be different, okay? So let's keep this by default, but for the collector efficiency and for the fluid parameters, we need to get the specifications of the device itself, okay? So it's, but what we can control, because we are architects, we are designing the building, we can control the number of collectors, we can control the slope, and we can, yeah, so the number of collectors and the slope. This is the thing that we can control. The rest of the things depends on the system itself. What about here? We are in the location, northeast, the water volume per collector area, 2 gallons per square foot. It's good. The fuel. Okay, so that's important because we need a backup system. In the event that we don't have any sun, like, well, today, and we need hot water, so we need a backup system. So what is that backup system? It can be gas, it can be electric, it can be oil, or other. Let's use electric because in our building, we are going to use electricity for the rest of the systems, and we have a backup electric heater just in case if we don't have enough sun, okay? The efficiency of fuel usage. Okay, we can keep that. The daily hot water usage, that's important. We are thinking of 80 gallons. Okay, so we don't need, okay, no. That's another parameter that we have to include here. Daily hot water usage. So what's the daily hot water usage? That's why we need this table, okay? So apparently we have 15.8 gallons per person per day. So if we have 4 people, we can use 15.8 gallons per person and per day times, if we have 4 people, so that would be whatever, 32. Me llegó una 4 por 5, 20. Es. Use the calculator. So this is 15.8 times 4. 63. 63.2. 63.2 gallons. Here, by default, we have 80. Okay, so let's type 62. Water set temperature, I explained this. We need to heat up water up to 140 Fahrenheit because at that temperature we kill dangerous bacteria. So if we want to have safety, we need to heat up water up to 140 Fahrenheit. It's too much, so we can hold this temperature, or we can stay under shower at 130 for a few seconds. After that, our skin will be damaged, okay? But at the tank, we have to heat up the water at this temperature because we want to kill the bloody bacteria. And then the environmental temperature, 68 Fahrenheit. Okay, that's important because that affects the efficiency of the water tank itself. If we have the water tank inside the house at a comfort temperature, the environmental temperature can be 68 Fahrenheit. If we have the water heater or the storage tank in the basement, and we don't have a heating system in the basement, this temperature can be lower. Okay, so imagine that on the basement, we have 50 Fahrenheit. And this is the UA of auxiliary storage tank. This is the thermal insulation of the storage tank. Okay, so the storage tank. If we analyze the storage hot water tank, this is a section, okay? So we have a device like this. And if we have a section, we have thermal insulation. So we have two metallic plates made of aluminum or galvanized steel or whatever. And this is the section. So we have thermal insulation. This yellow stuff is the thermal insulation of the storage tank. Depending on the thickness of this thermal insulation, we can change this value, the UA. Okay, so that's the U value and the area of the storage tank. Probably this is something that we have in the specifications of the storage tank. We can leave this, but the environmental temperature matters, in that if we have the water tank in the house, we will have a temperature that is comfort temperature, 68, 70 Fahrenheit. If we have this storage tank on the basement or on the attic or a place in which we don't have a heating system, then the temperature will be lower, and that will affect the efficiency of that, okay? And well, those are parameters that we can't change. So let's do it. Okay, so basically it's very easy. We need the amount of solar collectors, we need the slope, we need the location. Water volume per collector area is always 2. We have to select the backup system that we use if we don't have sun, and the daily hot water usage that depends on the use of the building and the number of people. The rest of and we can change the environmental temperature. That depends if the water heater is in a comfort space or a heated space, or it's in an unheated space. So when we have this, we can run, calculate, and it takes seconds. And this is the interesting thing about the analysis of this. Okay, so we have a monthly, and then here we have the yearly. And the most important thing is that F value, the software is F chart. So we have to calculate this F. So what is the F? Is the fraction of domestic hot water that we cover with our system. So the average is 0.55. So that means that half the energy that we need throughout the year is covered by the system itself. We might think only half. Well, half is a lot, okay? But okay, we can be more ambitious. But we have to be careful, okay? Because look at this. In winter, only 20% of the energy is covered by the system. In summer is more than 80. It makes sense, okay? Because in summer, we need more, in summer, we have more hours of sun. So we have the ability to heat up water during the day. But in winter, we have only a few hours of sun and we can't heat up a lot of water. Okay, so how can we change that? Now that we have set the parameters, what can I do? I can change the slope. So let's type here 45 and see what happens. Let's calculate again. It doesn't change a lot. So the average yearly, it's 0.55, 55%. So everything that it's between 30 and 45, it makes sense. If we have something that it's something that will not work, imagine that we have a collector slope of 0. Then we calculate that and we decrease the, especially in winter. So we have, when we have a horizontal device, it's 0. Okay, so we don't generate any. In summer, it's not bad, but in winter, in December, it's 0. Okay, so it doesn't make any sense using a 0 slope. So everything that is from 30 to 45, it's good. Okay, so we calculate and yeah, so 35, it's slightly better than 30, so we can change the angle, but from 30 to 45, it's the, yeah, so it's the right area or the right slope. What can we change? What else? Can we change the daily hot water usage? Well, we can't change that because if we have 4 people, we can do that. What else can we use? We can change the number of collector panels. So let's place 6. Okay, so if we do that and if we calculate, now the numbers are getting much better. Okay, so now we have 70% of the total yearly domestic hot water usage covered by the system. I don't know, that depends on the building code. I told you that in Europe, those systems are mandatory. So if you are designing buildings, you have as an architect, you have to integrate these kind of solar collectors. I come from Spain, so in Spain, we do have to integrate solar collectors, and we have a limitation about this F value. So the F value has to be more than 0.6, more than 60%. So 0.7, it's good. No. Okay, so, but I don't want you to think about codes or regulations or building codes or whatever. It's about what we are doing here. Okay, so if we have more than 70% of the domestic hot water covered by the system, it's really good. But we have to look at this. Okay, so when we have 1, that means that we cover 100% of the domestic hot water that we need. That's good news. Okay, so every single drop of hot water that we are consuming in the building is so the energy comes from renewable sources. So that's perfect. But if we exceed the 1, we can have the overheating problems. Okay, so that's why I would keep always slightly below 1. So if we have 5 solar collectors and we calculate it again. Okay, so with this element, I only have 64%. I don't have 70%. And here, instead of 1, I have 0.92, 0.93. I would be safer with this option, because if we have 1, there's a risk of overheating. We can prevent this overheating from happening as well. But yeah, Here I'm on the safe side because I'm generating 94% of the energy, so almost 100, so that's fine. And that means that we don't have the overheating risk. Having a 1 value means that we have the 100% covered, but there's a risk that the water is boiling inside the pipes, and if the water boils inside the pipes will burst. Okay, so anyway, how many collectors? 4 is, well, we have 56%, but there's room for improvement because this is 0.8. 5 is good enough. 6 is a little dangerous because we have 2 months, June and July, with 1. Once we surpass this value 1, we don't know if it's dangerous or not, but there's a risk that it can be dangerous. Okay. If you can say, okay, let's put 10 solar collectors. Calculate. Okay, so 80% of the yearly energy is covered by the system, but we have a lot of 1s here. That is great, but in this case, we need a plan for those months in summer in which we have a risk of overheating. So that's fine. Can we make it even better? Yes, so let's make it 12. Okay, so with 12, we keep growing and we keep increasing the amount of the percentage of yearly energy that is covered by the solar system, but we are running more risks using this or having a lot of months with an excess of hot water. So it's not about, okay, so how many solar collectors can I place? 20. We have to think about it. If we do this, there are things we can do. Probably we can increase the water volume per collector area. So let's increase this to 4 gallons per square feet, see what happens. I think we have 1. Yeah, it's not. So let's do this with 10. This would be something outrageous. Okay, this parameter must be between, so 7 is maximum, apparently. Okay, probably the numbers are getting better. And what happens is that we reduce the risk of overheating. Okay, so this is something we can do. We can increase the gallons per square feet, the storage capacity. Okay, so we can do that, but 2 is because if we have 7 gallons per square feet, we would have a huge tank. Probably it takes up a lot of space. So let's keep it with 2, and let's deal with this. Okay, 12 solar collectors is too much. I think 5 or 6 would be the optimum. And now we can use the monthly plot, and there are things that we can plot here. Okay, so we can plot the domestic hot water, the auxiliary, and the F. We're going to use this one. Okay, so what is this? So that's the domestic hot water consumption. Okay, so we have January. In February, we have less domestic hot water because we only have 28 days. And then that depends basically on it's the same throughout the year, the water consumption. It depends whether we have 31 days or 30. We have 31, 30 days. Here we have June, July and August with 31, then September, October, November, and December, okay? And here we have the domestic hot water consumption in February. And I'm going to plot only the auxiliary. Okay, so what is this? Here we have plot 1 and plot 2. So what is the auxiliary? Is the amount of energy that we need. And it makes sense. So we need more energy in winter, and when we have two values, when we have one in June and July, okay, so here we don't need any auxiliary energy. So that's the energy that we need as a backup when we don't have enough sun. And then finally, we can plot the F value. So the F value, it's the other way around. That's the percentage that we cover with our system. So in winter, we cover 30%. In summer, we cover 100% of everything. Okay, so what shall we do? We can print out can we plot monthly plot? Can we print? No. Okay, so I think the best option would be to take a screenshot. And place it here. Okay, so here we have this is the auxiliary, and this is the domestic hot water. Well, I don't know. I think the F is the right thing that we need. We're going to paste this one too. The auxiliary energy that we need. Okay. So that would be the outcome. Usually we have the F value. This is what we need. And if this is above 0.6, it's a good system that we have designed. If it's below 0.6, it's not enough. If it's above 0.6, then you have to be careful with the 1. Okay, so I think in this case, if we follow the curve, I don't think there will be something weird here. Okay, so I don't think we will have overheating problems, because looking at the curve, I think the peak will be very close to that one. But if we do this, if we change this to 12, and we calculate again, and we plot the F value, look at this. Okay, so if we follow the trend, the curve is going like that. So probably here we might have problems of overheating. So I think the one with 6 solar collectors is the best one. What the hell is that? Yeah, I think that one is the best. Okay, so are we done with this? Not yet. So what do we need? First, solar collectors. We need to calculate the collector area. So that's the collector area that we need. but we can have 68 if we have a 20 square foot panel. We have 4 solar collectors, or we have each solar collector is 20. So we need like 4 solar collectors. So the final area would be 80. The storage, it would be 80 times 2, 160 gallons. And the daily hot water usage, we have this table. So it depends on the number, on the kind of building that we're using, times the number of people. So around 63 gallons. Okay. Then we have to go to the PV watts, and we have to change all these parameters here. I mean, it doesn't do any harm if we take a screenshot of this. That will make me understand that you have the right values here. Okay, so with these tables, I can see that you have changed the number of solar collectors and the location and the water to volume collector area and the slope. Okay, so yeah, so I think that would be the outcome. You have to copy the parameters that you have changed, and then the outcome, the table, and the graphic of the F value and the auxiliary energy that we need on a monthly basis as a backup for the solar collector system. Finally, here we can, in preferences, we can use with the economics on. And what is this? We have cost per unit area. So here we have the dollars per square foot of solar collectors. By default, we have 15. We have the price of energy. This is the price of energy. If we are using an electric system, we have used the electric system. That's the price of kilowatt hours. Dollars per kilowatt hours. 0.04. This might be in Texas. What is the price of kilowatt hour in New Hampshire? I think it's I think we calculated that a few days ago. Yeah, it's around 20 cents per kilowatt hours. Okay, it's 50% higher than the national average. So if we want to run this economic analysis, this would be, it's not 0.04, it would be 0.2. It's 20 cents or $0.2 per kilowatt hours. Okay. Then annual increase in electricity, price of natural gas. We should price of oil. Okay, so there are a lot of. Do we have a? Do we need a mortgage to do this? The mortgage is 20 years. What is the interest rate? There are a lot of things that if we were studying business management, all these parameters would be relevant, okay? But we're not studying business management, so we are not going to do that. So we're not dealing with the economic analysis, but this is a right tool if we know, if we can predict the interest rate in 20 years. I can. We can use this tool to see if that makes sense or not. We can calculate, and in the economic summary, we have this. Okay. credits, interest, life cycle, investment, life cycle savings, first year savings, initial investment. Okay, so according to this, the first year fuel cost will be 553. The savings, we are saving 1,000 or 1,350. The initial investment is this. Okay, so if the initial investment is 2,300 and we save 1,300 per year, that means that by the second year we can make money. And then the life cycle savings is a 20-year life cycle. We save 28,342. And here we have the mortgage, the whatever. I think we did this with PV panels, and usually the return of investment in PV panels is long term. So we are talking about 10, 12, 14 years. The return of investment of these solar collectors is much better. Okay, so it's more because the technology is cheaper, basically, and the efficiency is higher. Here, the efficiency is around 70%. It's more with evacuated tubes. The efficiency of PV panels is around 10, 12%. Okay, so efficiency is the amount of energy that we convert from the sun. So 70% of the energy from the sun is converted in hot water. In PV panels, only 10% of the energy is turned into electricity. So that's the efficiency. So that's the economics output. So that's very efficient, and it makes sense because it's very cheap. The technology is very cheap. Okay, so the PV panels is way more expensive. Here, what we have flat plate collectors. I told you that you can go to the Home Depot and manufacture your own flat plate collector, and we need a water tank. It's something that it's not too expensive. Okay, but anyway, we should be aware. I can be aware of the price of the electricity right now. I can see the price of natural gas right now. It depends on the state. It's not the same worldwide, but and the annual percentage of increase of depending on the fuel, the electricity, the natural gas. This is something that I can predict based on the trend over the last 20 years. But then with the mortgage and all that stuff, it's but if you are into this, you can use this tool to predict but usually for the PV panels, the return of investment is more than 10 years. With solar collectors, it's between 1 or 3 years, something like that. So it's a safest investment, this one. Then it has risks of freezing, of overheating, all that stuff. So we are not going to plot, or we are not going to print the economic analysis. But before that, I need to know what you are doing. Okay, so what are we doing here? So that's why we have to come back to this one. We are using a solar water heating system, and we are using this option. Okay, so at least this is what we have calculated. We have calculated the system just for domestic hot water. So with this system, we have flat plate collectors. We have flat plate collectors. We have, well, by the way, here, yeah, we have the fluid specific. So we are not using the direct
circulation system because we have this antifreeze fluid here with a water tank. Yes, so that's what we are using. So that would be the outcome of this first exercise. But I want you to do this with the building that you're analyzing. Okay, so on Wednesday, we will finish modeling the building in Revit if we haven't finished yet. If you're working with your capstone project, you have to start making these assumptions. How many, if it's a residential building, how many apartments you have? How many people? What's the domestic hot water usage? We will have hot water in that building. And you don't need to know the final design to have an estimate of the number of people and the hot water usage that we have in this building. And then you need an estimate of the amount of area that you can use, and we will calculate this. Okay, so we can use this system. It's the easiest one. We will have solar collectors, water tanks. We can debate if we have individual water tanks in every house, or we have a general water tank that supplies hot water to the whole building. We can talk about that. But that is what I need by Wednesday. Okay, so by Wednesday, I will open the assignment. And I need at least this information about your building. If you are working with a single family house, probably we can have 4 people or 6 people, depending on the number of bedrooms. If we are working with apartment buildings, those numbers would be larger. And so you have to deal with this software, and we have to start analyzing how many solar collectors we would need to cover up to 70%, 60 to 70% of the hot water usage. And we can have as many solar collectors as we need. So at least we need to know with the available area how much hot water we can cover with our system.